So I have started recording. Anyway, so okay. So suppose this x vector has basically n component. This x1, x2 up until xn is are all random variables, and I now define a distribution that is the n-dimensional generalization of the uh, Gaussian distribution. So this is fx with parameter mu and v. This v is a matrix, is an n by n cross n matrix. Okay, so this v is a n cross n matrix, usually symmetric and actually symmetric. And so this would be given by 1 by 2 pi all to the power n over 2 mod v to the power half. This mod v basically means a determinant of v. Okay, so v is a matrix, and this is the determinant of v, and then exponential minus half, and x minus mu transpose v inverse, the inverse matrix, x minus mu. Okay, so this is my distribution in terms of x1, x2, blah 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 to xn. So this x vector here simply tells you that there are n number of random variables, x1, x2, and so on and so forth. And this gives you the probability of finding simultaneously x1 between x1 and x1 plus dx1, x2 between x2 and x2 plus dx2, and so on and so forth. Okay, so this gives you that. Now if you calculate the respective expectation value and variances, then you will see that the expectation value for the ith random variable, which I call the expectation value of xi, that would be equals mu y, and the variance of xi will be VII. This is the diagonal elements of V would be just the variance of the ith random variable, and the Vij is the covariance. So the covariance matrix, the covariance between xi and xj will be given by Vij. Okay, so so this is the definition, and you can easily check that for n equals 1, it reduces to your usual Gaussian distribution. Okay, so just for one random variable is just x minus mu times x minus mu is x minus mu whole square. V inverse is basically 1 by sigma square. Okay, if there is this, and this is square root of 2 pi, and this is sigma. Okay, and that's it. So you have mm, this definition of Gaussian distribution for n-dimensional generalization. Now to give you some more example of other distributions, there are a couple of distributions that would be important in our in basically in particle physics studies. So let me somebody mentioned exponential distribution. This is useful for whenever there is a radioactive decay or any exponential distribution law. You are trying to find out the mean penetration length of a radioactive radiation, and so on and so forth. In an appropriate unit, any exponential law, whenever you have an exponential law, it is usually normalized to an exponential distribution. The definition of the distribution is fx with the parameter tau, and this is given by 1 over tau e to the power minus x over tau. Okay, so it depends on and the region that I am interested in is x is between 0 to infinity. Okay, X is positive by definition. So if this tau represents time, then this tau can be, sorry, if this X has the unit of time, then this tau can be the mean lifetime. If this X is the has the unit of length, then this tau can be the average length, that the average penetration length of a radioactive particle, or the range of this particle. So remember this. So if X as a dimension of time, then usually this tau is called the uh, mean lifetime of the substance that is decay. Okay, or if X has a dimension of length, then tau usually interpreted as uh, the average range of the particle beam that you are considering. Okay, so for this distribution, again, if you calculate the expectation values, so the expectation values of X turns out to be just tau. So that basically reaffirms our intuition that this tau is some kind of an average. Okay, which is nice. And then this Vx, if you calculate, okay, so Vx would be given by 1 over tau integration 0 to infinity x minus tau whole square, and a to the power minus x over tau dx, and this thing will turn out to be tau square. Okay, so as you can see that uh, the mean and variance are both controlled by the same quantity, which is tau. Okay, this is one distribution that is often very useful in our mm, study of particle physics. And there is another which we call, uh, so in particle physics we call it to be the Bright-Wigner distribution, but maybe traditionally it is called the Lorentzian distribution. Okay. So the Lorentzian distribution, the distribution function is given by fx equals 1 over pi and 1 by 1 plus x square. Okay, and then so this is the standard Lorentzian distribution. Okay, if you integrate this thing, and the form that is useful in particle physics. So in particle physics, the structure that you often encounter is this. Okay, so this should be given by f, the function of some distribution that has the function of energy, and with parameter gamma and this E0, or I will call it, let's say, m, two parameters, gamma and m. This will be given by 1 over pi gamma over 2 divided by gamma over 2 whole square plus e minus m whole square. Okay, so this is the structure that we sometimes use. So here basically you can move from here to here by defining, I guess, x equals e minus m over gamma by 2. So if you you can try to move from here to here by defining x equals uh, e minus m over gamma by 2. Okay, so if you define this, then you can go back to the usual Lorentzian distribution. But this is the form we will often find it to be. Okay. Now, first of all, you must understand that uh, although the function is well normalizable, but the mean and standard deviations are not well-defined properties for this distribution. Because if you try to, let's say, integrate x fx, okay, let let me call this x fx. So x fx goes as x divided by 1 plus x squared. Okay. Now you notice uh, you might be prompted to write that if I integrate this between minus infinity to plus infinity, of course the range of x is from minus infinity to plus infinity, and dx, since this is an odd function, so it should be 0. But you should watch your mathematical steps very carefully. I mean, we usually do these kind of things, but here, mathematically speaking, it is not well defined. The reason is uh, the integration value. So this can be broken up into two parts. One is 0 to infinity x fx dx, and another piece is minus infinity to 0 x fx dx. You are saying that these things are equal and opposite, okay, and you are canceling these two. But remember, these individual things are going to infinity, because x fx, if you check this, so this quantity x times fx, this thing, this moves as 1 over x for x much greater than 1. Okay. So if when x is large, that means you can take this, you can ignore this 1, and this x square remains, and this x by x square is just 1 over x, and this. So if you integrate this thing, if you integrate this 1 over x, you just get log x. So both these integrands are logarithmically divergent if you calculate. And what you do is that you are just considering the two, you are basically canceling two divergent pieces and saying it to be 0. So we uh, usually we do not attempt to define the mean and standard deviation for Lorentzian distributions. Okay. So then, what is the use of this Lorentzian distribution? The Lorentzian distribution, or rather, let's say Bright-Wigner distribution. So in particle physics, we see this thing. So this is the Bright-Wigner distribution. You will see very often that the scattering cross sections comes out to be this form. So the scattering cross sections of a 2 to 2 process. Suppose I will. Hello.
Hello, sir. In numerator, there should be square of gamma by 2 square or not?
Square of, no. Here it is only gamma by 2.
Okay, sir.
Okay. Uh, all right. So basically, suppose you are considering thing scattering process. So the use of this Bright-Wigner distribution in particle physics, how you do. So you have uh, suppose this process. We are considering this, let's say E minus E plus electron positron collider to mu minus mu plus. Okay. Uh, so E minus E plus annihilating and getting mu minus mu plus. So this is the scattering that we tried to look in the large electron positron collider in lab. Okay. So how will this progress? Again, I will appeal to some of your idea about QED and field theory. If you do not have that, that's fine. I mean, you will not follow this part of the lecture, but that will not affect your overall understanding of this course. Okay. So the point is, this can occur in in two different ways. Okay, as long as you are looking at the standard model. So if you draw the Feynman diagram, again, people who are familiar with this kind of thing can follow it, and then you have uh, you have this mu minus mu plus. Okay, and this intermediate thing is either photon, or if you believe in the standard model, is a Z. Okay. Now, when you calculate the Feynman amplitudes of this thing, so this is an S-channel process, okay, and in the denominator of this propagator, you have a Q square, okay, in for a gamma, you have how do I put it? You have just 1 over Q square, where Q is the momentum transfer, and here is the S, and plus there is another term which falls off as uh, say like S minus mz square. Okay, this S is the Mandelstam variable. So this is like, so that I put it this way. This is 1 over S, and there is 1 over S minus mz square. I'm being very sketchy here. You should complete the calculation. I will see. All right, and mm, you should complete this calculation. Actually, I mean, people who at least know quantum field theory, those people. Okay. So suppose this Z boson was not present, then this S is basically 4E square. Okay, and if uh, it is the Z is not present, then if you plot the cross section with energy, so what you do is that you plot the cross section sigma of E plus E minus to mu plus mu minus, okay, and here you tune the center of momentum energy of E plus E minus system, okay. So basically you are scanning through the energy, okay. You are giving all possible values of energy, and so initially when you are at too low values of energy, then you will see this Z boson will not contribute at low energies, okay, and the cross section kind of drops as 1 over E squared as expected. Then if there is a Z boson, let's say if there is a Z boson, that is uh, you have a dependence like this, then in the neighborhood of the Z boson, the cross section will behave like this. Then this will so this will have a maximum at E equals m, and it will have a width of gamma. Okay, more is the gamma, more spread it will be, and uh, it will be peaked at E equals m. So E equals m, it will have a maximum, and it will have a gamma. Okay. So then suddenly, so if there were no Z boson, then it should fall like this. It should go on like this as you increase energy. But if there is a Z boson, then you will see that at some point it takes a peak, and then it goes as like this. So this comes as basically a peak due to the Z boson. Okay, and the energy at which this peak is you find, you call this the energy corresponding to the mz mass, the jet boson mass. And how wide is this distribution, okay, will give you uh, a measurement of gamma. Okay, so how will you get gamma? So if you go from here to so from, let's say, how can I make it independent of gamma? Mm, okay, I will figure it out. I am not getting it here, but you will see that if you move to a certain distance from E0 along in this way or in this way, okay, then the distribution function will fall off by a certain amount, okay. And so if you say that my distribution functions falls off by half, by 50%, then this width would give you a measurement of gamma. It might not be exactly gamma. I have to check at what distance you might have to move to check this. And this is how you get your gamma. Sometimes it is related to this full width at half maxima or something like that. I have to check it out exactly, but you can get the idea from here. So this is the essential idea of particle physics, that you expect if there is a resonance, then this kind of distribution is expected. And if you ever see a resonance in your data, then from that resonance, you can infer about the possible mass and the possible width of this Z boson, okay, or this, let's say, new particle that you are observing. But one thing to remember is that the distribution function, like the data, is rarely this nice. It will not be this smooth. So you will have beans, right? So you never plot actually this sigma. You basically plot the number of events that correspond to this mu plus mu minus, and you divide this thing into energy beans that you measure it with. So the actual data, so actual data will be looking like this. Okay. So you will plot the number of mu plus mu minus event. Okay, number of, let's say, the total mu plus mu minus event. You have to basically subtract the background as well. Okay. Now, so basically, in your energy beams are energy beams are have a certain resolution. Suppose, let's say, those are 1 GeV. So that means this is 1 GeV, this is 2 GeV, and so on and so forth. And in 1 GeV, you see this many events, okay, for 0 to 1 GeV. And then for 2 GeV, you see this, okay, and so on and so forth. And when you come in the neighborhood of mz, let's say at 90 GeV, then you see a histogram like this. Let me first draw the pic. You will see something like this. It would be nice if we could have the actual data. I will try to figure out the old LEP data, and we will try to analyze those data. Okay, and so this is the thing that this is kind of the histogram that you will expect. You get the idea, and then remember, in this, so whenever later I will be talking about signal and background, then in your mind you should try to visualize this kind of diagrams, okay, this kind of data. So these events, like if the jet boson was not there, if the signal events was not there, then there was still some probability to get E plus E minus, which is given by this area. Okay. So as long as I am trying to observe a jet boson, then this will constitute my background event, the background that I do not want. Okay. So these mu plus mu minus are coming from this photon channel diagram. They are not coming from the jet mediated diagram. They are coming from this photon mediated diagram. They are not coming from the jet mediated diagram. Okay. If I want to isolate my uh, uh, data of interest, then I need to figure out a way that what are my how to isolate my background events from my signal events. Okay. Okay. Usually this is done with Monte Carlo simulation. I will not get into the detail of that. But remember, on top of the uh, background event, there are some signal events, and from the strength, from how high these signal events are, okay, from this background event. So I have, if suppose I have estimated my background events, and uh, then I will try to find that how high these signal events are from the background event. I can try and make a quantitative remark about how strongly this E plus E minus coupled to Z boson, or where is the mass of the Z boson. So in practice, you will be given a data like this, your data like this. Then from this, you have to tell us that find the best fit value. So this is the usual phrase, best fit value for mz and gamma z. What is the, so suppose this is the height and this is the width and this is the average location, then what can you say about your mz and gamma z? So this will be our statistical data fitting that we'll be talking about later. But so this is one of the examples uh, by which you can do your statistical test. So remember, and these are cases where you have a concrete theory for your data. You have some expectation. You are not running your experiment in blind. You already know that if there is a Z boson, then my data will look like this, and the pattern that my cross section will follow will be given by this thing. Okay, so we want to see that, and if we see this or not, uh, after looking at the data, we can uh, conclusively infer on whether a jet boson exists, and if it exists, what is the possible mass and decay within the jet boson, and we can try to figure out many other properties in this way. So this is the statistical test that we will perform, or we intend to perform in the later part of the course. Okay. So now another very useful distribution that would be our bread and butter in statistical test is the chi-square distribution. So so the chi-square distribution for variable z would be given by this. So if z with parameter n, okay, and that would be given by 1 by 2 to the power n by 2 gamma n by 2, then z to the power n by 2 minus 1 and e to the power minus z by 2. Okay, remember the range of z is from 0 to infinity, and n can take only integer values, so n can be 1, 2, and blah blah blah, so on. Okay, so this n is sometimes called the degrees of freedom. So this is called the uh, number of degrees of freedom for the chi-square distribution, and it also kind of gives you the statistical average. So expectation value of z would be equals to 0 to infinity uh, z f z n dz. So this would be equals to n, and the variance of z, which is given by 0 to infinity uh, z minus n whole square f zn dz. This would be given by 2n. So if you actually do this integration, you will find these values. Okay. Now, why is this important? Okay. Again, this is important because of a very interesting theorem. It tells you that if there are n random variables and independent random variables, okay, so suppose there are n independent random variables that I denote by xi, uh, like I equals 1 to n. Do not confuse this with the multidimensional Gaussian distribution. So each of these are Gaussian distributed with mean mu y and standard deviation sigma I. So the distribution function of xi is f Gaussian xi with mean mu y and standard deviation sigma I. Okay, that means what I mean to say that xi is distributed as, hmm, how do I say? So xi would be distributed as uh, f xi with parameter uh, mu y and sigma I, that is 1 over square root of 2 pi sigma I a to the power minus xi minus mu y whole square by sigma I square, this 2 sigma I square. This is that, suppose the distribution of for independent random variable. Now if this is true, then the quantity z will be distributed I equals 1 to n. So this, I define this quantity uh, by over sigma I square. So I ask uh, how this will be distributed, how this z will be distributed. Okay. And the answer is this z will be distributed with as a chi-square distribution with n degrees of freedom. Okay, I'm not proving it. You should check. Okay, uh, and so there are a few things that you should notice here, just for intuitive understanding. This z, the way I defined, is always uh, mm, greater than 0, because this is basically sum of positive definite quantities. So since by definition z is sum of positive definite quantities, that means z by definition is greater than 0. Okay, now usually, okay, this xi is predicted from theory. Okay, suppose I tell you that my theory has predicted this xi for some reason. Okay. And this mu I and sigma I you are getting from data. Now, those if my theory is correct and I have gotten my mu I as a statistical average by summing up different random experiments, then it is usually true that uh, this distribution, this xi will satisfy Gaussian distribution because of the central limit theorem. Okay. Now, if my theory is very good and it agrees with the data, then I will have xi equals to mu I everywhere. So you can think about this xi to be two different measurement. Okay, let's say xi to be a measurement of Young's modulus and let the shear coefficient of the metal bar. Okay, there are only two variables. There is shear coefficient of the metal bar. Okay, and if the data, the agreement between theory and data is good, then this difference is small. Okay, remember. So if the agreement between theory and uh, data is good, then this difference is small. Then this difference is small. And this if your experiment goes haywire or your theory is wrong, then this xi is kind of everywhere and it will not agree with this mu I. Okay, so if the agreement is bad, then this will be reflected in this difference, and since this difference is squared, it doesn't matter if you are below the theoretical expectation or above the theoretical expectation, this square is always positive. So z will be away from 0 if your agreement between theory and data are bad. Okay, so suppose, so now you basically try to, so this basically gives you a tool to have a quantitative statement uh, between the quantitative statement about the agreement between theory and data. So this chi-square distribution, this thing enables you to uh, give quantitative statements about the extent of agreement between theory and data. Okay, so you notice the way I have constructed z is dimensionless. Okay, so it doesn't matter what kind of quantity that you are measuring, it does not depend on your dimensionality of the measured quantities. So by construction z is dimensionless, so it's applicable everywhere. So suppose if you take the chi-square distribution for n degrees of freedom, let's say n equals 5, you are again asked to draw chi-square distribution uh, for more degrees of freedom. Okay, so suppose this is z and this is, let's say, fz with parameter n. Remember, uh, the more is my number of experiments, like more is the value of n, there are more room to make error, right? There is more room to make error because you can make some error in the first data, you can make some error in the second data, you can make some error in the third data. So more are the number of experiments, you are more prone to error. That means the average value of z will increase as you increase this number n, and that's why you see that the average of this distribution kind of goes as n. Okay, so more sources of error you introduce, you kind of make yourself prone to make more mistakes, and all those mistakes add up because you are using squares here. So suppose I have 5 such measurements and I try to plot for n equals 5. Okay, and the plot might look like this, I don't know. Okay, so you should check plots of chi-square for many different reasons. Okay, now remember, the area under this is always 1. Okay, so the area under this distribution is always 1, and uh, I want to make a quantitative statement about the extent of agreement between theory and data. So how do I do that? So what I do is that I choose a cutoff point z0, okay, so that the area from z0 to infinity, this area from z0 to infinity, I call it, let's say, alpha. Okay, and this alpha you have to decide. Okay, suppose this alpha is, let's say, 10% or 5%. Okay, so this is let's say I have chosen this alpha to be 5%. So this choice of alpha will define a location z0. Okay, so that means that the probability of finding z beyond z0 is only 5%. Okay, so you can translate this into this statement. So if this z represents the extent of agreement between theory and data, then in view of data, in view of this mu I and this sigma I, Whether you will accept a theory or you reject a theory will depend on if you calculate Z from the theoretical input and the experimental outputs and check if this Z is greater than Z0 or Z is less than Z0. Okay. Remember, if this Z is greater than Z0, after you calculate your Z from a theoretical input, then you say, I would not say reject, you say do not, or rather, let's say reject the hypothesis or the theory with 1 minus alpha confidence level. So this alpha is 5%. If this is 5%, then this 1 minus alpha will be 95% confidence level. Okay. So remember, the smaller the alpha, the more confident you want to be. Okay. That essentially means you have to allow for more errors in the experiment so that you can be more confident about the statement. Okay. And if this Z is less than Z0, then you do not reject the hypothesis. You do not say, I accept the hypothesis. You say, I do not reject the hypothesis with 95% confidence level. That means the hypothesis has some degree of truth in it. Okay? So there you go. So there is how you make quantitative statement about the extent of agreement between theory and data using chi-square distribution. Okay. Now let us go back to this example that I was giving in the first class. So suppose you wanted to buy a ice cream parlor and mm, the previous owner gave you this data. So the a weekly distribution of this thing: Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and Sunday. Okay, and that person give you the percentages of this. I don't know, 2%, and then Thursday is again 10%, and Friday is again let's say 30%. Saturday is again 30%, and Sunday is the rest. I do not know how much this add up to. I hope that I have not crossed 100. So this is total is equals 100%, of course, if I have made this addition correctly. So this is the theory. So this is your theory. And based on the statistics, you actually try and calculate based on your running of the parlor for a few weeks. You have noticed that on Monday, let's say 253 people came up. On Tuesday, there were like 180, and Wednesday on there was, I don't know, maybe 50 people, and so on. And you got these numbers now. You actually counted the number of people who came. Now, based on this, and suppose you have fixed that you want to test the hypothesis of the previous owner with 95% confidence level. You want to see whether you can accept this hypothesis or you can reject this hypothesis. So what do you do? So remember, these are counting experiments. So the amount of error you make here, so suppose this is your X Monday. Okay? And that means, so this is your mu Monday, the average value of the people that came on Monday. And so that means the sigma Monday would
Sir,
be,
sir,
yeah.
sir, when we are taking data of a single day, I mean, how are we calling it average?
You have run it for several weeks, and then you are taking the average.
Okay.
Okay. And so since these are counting experiments, so the you expect the error to be square root of 253, let's say, because it's a Poisson distribution. Okay. And Tuesday it is again 180, and so on and so forth. And then again you actually calculate your z. So z will be what? X Monday minus mu Monday divided by sigma Monday square plus so on and so forth for every day. Now X Monday, how you calculate? So you figure out the total number of sample, the total sample that you got. So suppose you are sampling from around 2,000 people. Okay. So 15% of this 2,000 would have been your prediction for X Monday. So you substitute that as X Monday and add it for 7 days. Okay. Now you calculate Z. Remember, now you have to decide what are your degrees of freedom in this thing. So here degrees of freedom would be 6, because if you knew the number of participants on like theoretical prediction of 6 days, then you can infer about the seventh day. Okay, so the seventh day prediction does not depend, sorry, but does depend on the previous prediction. So here the degrees of freedom is usually taken to be 6. Okay. So now you calculate this thing, you have a data, you can calculate this thing, you have a number, I don't know. Suppose the number is 18.796. I don't know. You have to calculate, and this is the number, this thing. Then you actually look at the chi-square distribution for n equals 6. Now you figure out the z0 corresponding to which uh, this 5% is there. So usually there is a chi-square table. So you look, you search on Google by chi-square table, and it will give you a table, and that lists these values, these z0 values for 5%, 1%, 10%, these things. Okay, so that you don't have to calculate. You can use this chi-square table to conclude whether you want to accept uh, or do not accept, or rather reject or do not reject the previous owner's hypothesis. Okay, so
Sir,
that's it.
can you repeat why did you take n equal to 6?
Because the prediction for seventh day was not an independent prediction. Okay,
Okay,
because the total percentage is 100%.
okay.
Okay, so so this is how you do hypothesis testing, and these type of hypothesis where there are no unknown parameters. Okay, so your flux on Sunday, your basically number of people who show up on Sunday or Monday, it does not depend on any unknown parameter. You have absolute numbers for them. Okay, and these type of hypotheses are called simple hypothesis. I will come to those again later. And suppose you did not know the absolute number, but you know the numbers as a parameter of these numbers as a function of some parameters. What can these parameters be? So the parameter can be the seasonal average of the total number of people. So during the holidays, suppose there are less number of people in the campus, so these things would be less. And during say other time when the classes are in full swing, then the numbers would be higher. So you could have given the numbers not in terms of this percentage, but in terms of those parameters. Okay, and those parameters would be unknown parameters. Then you would be doing a different kind of hypothesis testing, and those kind of hypotheses would be called composite hypothesis if you have unknown parameters involved in your theory. Okay, so so this is essentially how you do hypothesis testing using a chi-square distribution. Okay, now, ideally, I would give you a break at this point, but since I do not have much left to cover in this lecture, I only one more thing that I want to cover. So let us continue, and then we can all finish at the same time. Okay. So just bear with me. So the last thing uh, I want to talk about is quite interesting, but not so let's say, not so much emphasized in during these kind of classes. In fact, I was not covering this in my previous versions of these lectures. Okay, so the idea is this. Suppose, so I kind of convinced you that everything at a certain limit reduces to a Gaussian distribution. Okay, and you often quote the uncertainties. When you quote the uncertainties in your measured parameters, okay, so I told you that suppose you are measuring, let's say, some quantity. I call this quantity, let's say, I don't know, so theta. So suppose you, and you are giving the measurement to be, let's say, 1.08 plus minus 0.03. Okay, you have the tendency of interpreting such uh, results in terms of Gaussian distribution. You say, so you have this Gaussian, you have this Gaussian idea of standard deviation, and you can say that to find theta in the interval between 1.08 minus 0.03 to 1.08 plus 0.03 is 68%. Okay? If it follows a Gaussian distribution. All right. And similarly for 2 sigma, so suppose you enhance this range, so minus 0.06 to 1.08 plus 0.06. So this would be 95%. Okay, so it is only true if it follows Gaussian distribution, actually exactly Gaussian distribution, right? Now, what happens if it does not follow the exact Gaussian distribution? Okay, so suppose if it has a longer tail than the Gaussian distribution, then maybe the this error bar uh, that I am suggesting here, that it is within 2 sigma of the mean, is not 95%. But if it is a flatter distribution than the Gaussian distribution, so remember all these words that I am saying here, try to visualize. So if it is a, suppose this is my Gaussian distribution, it's a standard Gaussian, and suppose this is another flatter distribution. So since this is spreaded more, then that means the probability of finding theta between these interval will be less. Okay. Of course, this is true if I do not know the distribution exactly. But how less can it be? Okay. Suppose for any arbitrary distribution, can this even reduce to zero? That, or there is a limit up to which it can reduce to. Okay. That is the thing that I am trying to figure out here. Okay. So given any distribution, so by any distribution I mean that the distribution can be anything as long as it satisfies the normalization condition over whole space. This is equals 1. Okay. Suppose I am drawing any distribution of this thing, of this kind. Okay. Suppose this distribution is anything. So this is my fx, and this is my x, and this is any stupid distribution that you can possibly think of. Okay, so this is my distribution. Now, this distribution, usually, if it is like a well-behaved distribution, it can have a mu. Suppose after you integrate, you get a mu here. Suppose this is your statistical average. So this is your expectation value of x. Okay. And it will also have a well-defined sigma. So I call sigma square to be variance of x, okay, which is essentially integration of x minus mu whole square fx dx. Okay. So sigma square is also well defined. So I choose any arbitrary distribution with mu given by this and sigma square given by this. Then my question is, what is the probability that uh, doing a random measurement on x will give me a value that is outside k sigma from this mu? So what I mean, suppose I go to here, so I call it say this is mu minus k sigma, and I go to here, okay, this is mu plus k sigma, okay, and so this is my average mu, and these are my sigmas, okay, and this is the k is a positive quantity, okay, k is a positive quantity. Now, what is the probability that uh, my random choice of x will lie outside this region? That means in this region or in this region. Okay. So I want to know what is the probability that given any arbitrary distribution fx, I want to know that what is the probability that a randomly sampled x will lie k sigma away from this mean mu. In essence, what I am trying to find out is probability of x minus mu, mod of x minus mu, to be greater than k sigma. Okay, and what is this? Now, if I want you to take a guess, can you tell me with any confidence that how can I possibly figure out this value if I do not know this fx distribution? All right. But there is an inequality. It tells you, of course, the probability of finding it outside would be something. For Gaussian, the probability is very small if k is large. And for other flatter distribution, it will be larger. But how large can it be? Can it be 1? Can it be so that you get this to be 1? The answer is no. There is an upper limit to it. Okay, so the probability to find x minus mu beyond k sigma would be less than equals to 1 over k square. Okay, no matter what is the distribution. Okay. No matter what is the distribution, probability of finding x minus mu to be greater than k sigma would be always less than 1 over k square, and this thing is known as the Chebyshev inequality. Okay, and to convince yourself that this is indeed true, it is quite easy. So see, what is your sigma square? So sigma square is ideally, let's say, minus infinity to plus infinity, x minus mu whole square fx dx. Okay, so you can break it down, this integration, into two parts. So suppose you are doing this integration. So first you do this integration, let's say in this cyan region, and then in the red region. So you do this integration in cyan region and in red region. So for the cyan region, I will write down, so the region is defined by x minus mu less than k sigma, then x minus mu whole square, x minus mu whole square fx dx, plus the red region integration will be x minus mu mod greater than k sigma, oops, greater than k sigma, and then x minus mu whole square dfx dx. Okay, so now remember, both these things are positive definite quantities, because x minus mu square is positive definite, so and fx is positive definite and at every point, because it's a probability density. So if I just drop this term, and then I can change this equals to sign with greater than equals to, right? So this should be greater than equals to just the red integral, because this is positive definite. So this is positive definite, the non-negative thing. So this must be greater than equal to the red integral, which is uh, x minus mu mod of x minus mu greater than k sigma x minus mu whole square fx dx. Okay. So now I want to do this integral. Okay. So remember, so on the left hand side there is a greater than equals to sign. So some sigma square is greater than equals to this. Now in this region where x minus mu is greater than equals k sigma, what is the minimum value of x minus mu whole square? So in this region, in the red region, where x minus mu is greater than k sigma, mod of x minus mu is greater than k sigma, what is the minimum value of x minus mu whole square? So the minimum value of x minus mu whole square occurs when x minus mu sticks to the minimum value of k sigma. So the minimum, so in this region, the minimum of x minus mu whole square is just k square sigma square. So the integration has a minimum value of, if I take this to be k square sigma square everywhere and I take it out, then times fx dx, right? Because I am taking the minimum value of x minus mu whole square everywhere in the region of integration. I'm taking it out, and then the thing that is left is this fx dx that you are integrating over. Okay, and this thing also is less than equals to 1. Okay, so the this thing, so basic, sorry, so this is fx dx, then I have, sorry, x minus mu greater than equals k sigma, I'm just talking about, and this is my desired probability. I'm sorry, this is my desired probability. So this is the probability that x minus mu will be greater than equals k sigma. So I find this probability times k square sigma square is less than equals to sigma square. Okay. So if I invert this relation, this is p probability of x minus mu greater than equals k sigma should be less than equals 1 over k square. Okay, that there goes the proof. Okay, so remember, even for any arbitrary distribution, as long as it is well normalizable and the mean and standard deviations are well defined, the probability to find the random variable x away from mu by k sigma cannot be arbitrarily large. Okay, it must be less than equals 1 over sigma square, or 1 over k square. Okay, so this k is this. So basically, suppose for the 2 sigma limit, so if you are considering 2 sigma limit, then p of x minus mu, let's say, greater than equals 2 sigma, that is x is 2 sigma away from mu, is less than equals 1 by 4, that is 25%. Okay, so you see that the Gaussian distribution is well within this limit, because 2 sigma is 95% confidence level. So that means this, the value of this for Gaussian, this value is almost 5%, which automatically satisfies this 25% bound. So even if you don't know about the exact nature of the distribution, you can always say something about the probability of finding x away from mu by 2 sigma using this inequality. And by comparing these numbers, this 5% and 25%, you get an idea that this Chebyshev inequality is kind of a conservative bound, and it is so relaxed compared to Gaussian or anything else that we know of, that it is rarely useful. I mean, it is, let's say, it is too loose to be of practically any use. But it is good to know that even if you do not know your distribution, you can always put a bound on the probability of finding a random variable x k sigma away from mu. Okay. So with this, I will stop, and let me know if you have questions up until this point. Okay. All right.
Sir,
Yeah.
means once you can repeat about central limit theorem, like we discussed, like if we are adding random numbers or random distributions, any distribution, it has to like diffuse to Gaussian distribution. Means what's the theory behind it? Means can you little bit tell us?
Uh, yes, I will talk about that when in the probably in the next lecture when I talk about characteristic
Okay,
functions.
sir. Okay, sir.
Okay.
Sure. Thank you.
Okay. Yeah. Anything else other than that? Yeah. In the meantime, you should try and plot the chi-square distribution and check that the sum of Gaussian random variable actually follows a chi-square distribution in the way I defined the chi-square variable, that is x minus mu whole square divided by sigma square. Those things follow a chi-square variable. Okay. And in the meantime, I will be trying to find out some actual data from experiments. And when we do the statistical test, it would be nice that you can write the codes live, even if it takes time, and try to do some data fitting. And you can write the code in whatever languages you are comfortable with, and we will try to give you the algorithm and then try and implement those algorithm in your codes and show everyone how you are doing. And all of you should actually try to do this in your home. I see that some people are doing and some people are not doing. If you do not actually see this explicitly in your codes or in your computer, then I am not sure that your learning will be complete. Okay, and it would be difficult for you to have a good idea um, of what is being talked about. Okay, so it is better to do these simple exercises. I mean, these are not very complicated. You can take help from your friends here. At least do it. Otherwise, you will not have a good feeling. Okay. So this is not statistics is not something you just learn in the same way you learn a physics theory. Uh, you have to actually do it to learn it. Okay. So you do that. That's my only suggestion. And I will schedule the next class in Google Classroom. Okay. Okay then. Bye.
Bye, sir.
Bye.
Thank you, sir.
Bye.